Hello and welcome everyone. So this video is going to be a solution walkthrough to the first exam in intermediate micro. And it's basically going to cover consumer theory. So the first 5 or 6 chapters in Varian's intermediate micro is basically the coverage, although I don't follow Varian 100%. But this is pretty close to Varian for this exam. Same with all my solution videos. What I'm going to do is I'll display the exam as I am here. So you can see the questions if you want to remind yourself what they were and or try them for the first time for yourself if you take a screen capture or whatever. The first 3 were multiple choice. Whoop, I can't remember if I cut that one off or not. All right, fine. So then there's a bunch of longer form, what I'll call mathematical essay questions. Right? Okay. I know this part's just terrible, but I can think of no better way to be able to do this than to just go over the video real quick. All right, cool. So here's the last one. All right, so now I'll go to the solution. Solution for the first 3 were C, D, D. For the first one, if I truly believe Coke and Pepsi are interchangeable, where X is Coke, Y is Pepsi, my preferences can best be represented by which of the following? All right, so here we have some information about preferences. We have to fit it to a utility function or fit a utility function to those preferences. The first one's Cobb-douglas if alpha and beta, the coefficients are 1. The second one is perfect comps, that's not right. The third is a monotone transformation of perfect subs, which will actually represent perfectly substitutable preferences. So that's just fine. The answer is C. D is incorrect. Without a budget constraint, we can definitely represent preferences of the utility function. We just can't find the optimal bundle. So in question 2, I show the perfect substitutes utility function. Getting to 3x plus 3y is a positive monotone transformation of this one. So positive monotone transformation is going to preserve the rank order of any bundle. So like pick a bundle, kick out a utility function, kick out a utility number. So it could be like 1 of each. So x is 1, y is 1, 1 plus 1 is 2. Good. You have another bundle, 2 of each. 2 plus 2 is 4. Okay, so my utility numbers are 1 and 4, saying that I like the second bundle better because the utility number was higher. If we triple everything, we're going to get what? 2 times 3, well, 2 and 2 is, we get 12, and then we'll get, it was 1 and 2, so we get 6, and then we'll get 12. Sorry, whatever. So the idea is any bundles that are ranked in one particular order will be ranked in the same order with its positive monotone transformation. Okay, so that was just sort of an aside. Extra value from this video apart from me stumbling over it. Fine. So for question 2, suppose the consumer has utility given by standard perfect subs and good X is money, good Y is pizza, saying that money and pizza are perfectly interchangeable. The price of pizza is $3. Price of money, well, it's just $1 for $1 of money, right? Consumer has $30 available. Which of the following is true? For perfect subs, what we need to do is compare the slope of the indifference curve to the slope of the budget constraint. We have our 3 friends, Alex, all X, Allie, all Y, and then the one where the budget constraint is coincident with one of the indifference curves. So the entire budget constraint is a solution. For this one right here, well, we can get the MRS, that's the marginal utility of X, divided by marginal utility of Y. The coefficients here is just 1 and 1, so the marginal utility of X is 1, marginal utility of Y is 1. So the MRS is 1, so indifference curves have the slope of 1, but the price ratio is 1 divided by 3, 1/3. So the budget constraint is flatter than the indifference curves, which gives us our Alex solution, all X. All X has the interpretation of the consumer's going to just keep their money. They're never going to buy pizza. All right, question 3, absolute value of Edith's marginal rate of substitution at current consumption bundle is greater than 5. So marginal MRS, marginal utility of 1 divided by marginal utility of 2 is greater than 5. Convex preferences tells us we have something kind of like Cobb-douglas. Currently consuming positive amounts of both goods tells us we have an interior solution. The answer is indeed D. Taking away some of good 1 and giving Edith 5 units of good 2 for each unit will necessarily make her worse off. I'm not going to go through each of these here, but I'll show why D is correct. You can do a similar argument to verify that the rest are incorrect. So I'm going to do this with a slightly different problem. Here, D is equivalent to 1 on this sheet. So this is for ors, whose marginal rate of substitution at the current consumption is greater than 3. Ratio of marginal utilities is 3. See, it's just like 3s versus 5s. Fine. Okay, so the answer is number 1, being that MRS is greater than 3 tells us we're on the vertical portion of the indifference curves, right? So the MRS has a slope greater than 1 on convex or Cobb-douglas utility function or indifference curves. When the slope of the indifference curve is greater than 1, we know we're on the kind of vertical portion, kind of like this right here. Okay, cool. So what we need to do is show that moving back 1 or moving left 1 up 3 places ors on a lower indifference curve, or Edith back 1 up 5 will be a lower indifference curve. And definitely ors will be necessarily worse off because the indifference curve is steeper as we move to the left, which means it's going to dodge away from where we're moving to, is the idea. So even if we assume marginal rate of substitution is 3 at the current bundle, so I drew a slope of 3, if I move over 1 up 3, I move to this bundle. So I go from the 0.29 to the 0.112 if I'm using this version of the problem. What's the problem? Well, if we take 1 away and replace with 3y, we necessarily are going to be on a lower indifference curve because basically, well, you know, I have the write-up right here, but basically the issue is if we're moving over 1 and then up 1 at this kind of constant slope, that's not what the indifference curve is doing. It's got an increasing slope. And so we're going to be on a worse indifference curve. Okay, fine. So that was question 3. Question number 4. Max insists on consuming 3 spoonfuls of Cocoa Puffs, good X, with exactly 2 spoonfuls of Honey Nut Cheerios, good Y. Write down Max's utility function. All right, so what I'm going to do is I'm going to get a list of the acceptable bundles. I'm going to start with the one that we know that they're going to like. That's this one, 3 with 2. So this is good X, this is good Y. We know for sure they're going to want the bundle with 3 Cocoa Puffs and 2 Honey Nut Cheerios. Good. And then what if we go 6 and 4, 9 and 8? So this will all work. Okay, fine. So I said 9 and 8. It's 9 and 6. Fine. So then just looking at my price list, or actually just inferring from what I've got right here, I can tell the relationship between good Y and good X is Y is going to be 2/3 times the amount of good X. Remember, if we have perfect complements preferences, which we know we have here because we're using exactly 2 spoonfuls of one good with the other, if you had the perfect complements utility function, you could replace the comma with an equal sign, solve for Y, and that'll be the ray through the origin that connects all the corners of the indifference curve. Well, going in reverse, we have that ray through the origin from what we're backing out right here. I can replace the equals with a comma and then multiply through by 3. And sure enough, here's my utility function. All right, fine. So now what I want to do is I want to find the optimal consumption bundle, given the price of good X is 3, or 8, price of good Y is 6. Find the optimal consumption bundle. Okay, fine. So I'm trying to maximize this utility subject to this budget constraint. Like I said, when you've got your perfect complements preferences, you replace the comma with an equal sign. Solve for Y, that'll give us a ray through the origin that connects all the corners of the indifference curves. What do we do with that? Well, one of them crosses the budget constraint. And basically to make that happen mathematically, we can substitute. So what I did is I replaced X for Y. So in my budget constraint, I have 8X plus 6Y. So I can write 8X plus 6Y. I can write Y as 2/3 X. And so I think I wrote this as Y right here. So that's why I was kind of paused for a second. I realized I got a typo here. It didn't affect the answer. I just wrote Y, but I should have wrote X. Okay, so sorry, that's an X. Fine. Multiplying through and then solving, I get X as M over 12. And then over here, oh, now my page is going to be blue. Great. So if I do the other substitution, if I solve this thing for X, that's going to be 3/2 Y, which I substituted in. Solve for Y, I get M over 18. What's Max's utility? Consuming the optimal bundle. This is the optimal bundle. Let me evaluate the utility function at the optimal bundle. So I plug in for X, M over 12, and for Y, I plug in M over 18, and that gives me this. It actually reduces to M over 6. Okay, and then part D, if the price of Cocoa Puffs were to rise to $10, what would be the substitution effect we calculate in absolute terms? Well, we did this exercise in class, but it turns out for perfect complements, there's no scope whatsoever for substitution. I have this in one of my IMX, in the IMX 1. I think it's the last question in the IMX video that goes over this as well. You could do this algebraically, but it's enough to just remember or just observe. For perfect complements, the substitution effect is 0. That's why it's really easy to calculate. All right, number 5. So consider a consumer with utility function x1 times x2 facing prices of 16 and 12, or 16 and 4. Find the cheapest bundle possible to attain utility level of 25. This is an expenditure minimization problem. So what we're trying to do is we're endowed with this utility function, or our consumer is. They're trying to hit this level of utility, and they want to do it as cheaply as possible given these prices. So what they're trying to do is minimize their expenditure. This is the expenditure on good X, or good 1. This is the expenditure on good Y, or good 2, right? So price times the amount, price times the amount. So my total expenditure is this sum. I'm trying to minimize that. Now, this is the Lagrangian. This is minus my Lagrangian multiplier. This is my utility function minus the target utility. So what I'm going to do is take the partial derivative with respect to X, partial derivative with respect to Y, or in this case, partial derivative with respect to good 1, partial derivative with respect to good 2. So it's just the coefficient, 16, and then here we're treating x2 as a constant with respect to x1. So I take that partial, just like if it was like a number, I'm going to be left with x2 times lambda. So that's what this is doing. Same thing when I take the partial with respect to good 2. This is just going to be 4 minus lambda x1. Right, so I can go ahead, I can solve this system of equations, and basically I get this relationship 4x1 equals x2, which I substitute into my constraint, which is this thing. So I'm going to replace x2 with 4x1. So that's going to give me 4x1 squared, right? My constraint is not my budget constraint. Here my constraint is I have to hit this level of utility using using this utility function, right? Okay, so these are perfect squares. I can square both sides, and then I end up getting 5 halves, or 25 over 4, right? And then if x, or good 1 is 2.5, then good 2 has to be 10, right? Because 4 times 2.5 is 10. Right. What must the consumer's income be in order to be able to purchase that bundle? Well, it's 80, so this is going to be price times the amount, price times the amount. So I basically just evaluated. I found the expenditure function. I just evaluated at the optimals that I just found. Okay. These are my Hicksian demands. These are not my Marshallian demands. The solution to the consumer's expenditure minimization problem are our Hicksian demands, functions of the prices in that utility level. My Marshallian demands would be functions of the prices in my income. All right, so anyway, question 6. Consider a consumer with utility function minimum x1 plus 2x2, and 2x1 plus x2 faces these prices, solve for the optimal bundle. Okay, so we can solve this using basically the same approach as any other Cobb or perfect complements, although it does have this like perfect substitutes flavor to it, kind of built in there. Fine, though, we'll just replace this comma with an equal sign, solving real nicely. That gives me x equals y, which makes this problem super easy. So now I can just replace y with x and replace x with y in 2 different versions of my budget constraint and solve for my respective amounts of good x and good y. Right? Now, if I had something else going on here, remember, if you have this type of, so the indifference curves for this type of utility function are not going to be right angles. They're going to be wings, right? So they're going to look kind of like this. And so the problem is, you could then have 5 different locations for the solution. So it could happen at the kink, at the corner, like where they come together, just like with perfect complements. It could happen at the ends, at either intercept, or it could be coincident with either one of those wings. So you could kind of discern which is the one by comparing slopes. Turned out that wasn't a factor here. All right, question 7, consider a consumer with utility 2x plus 3 natural log of y. This is quasi-linear. Find the optimal bundle if we have income 18, faces prices of 6 and 1. Okay, fine. So my marginal rate of substitution is the marginal utility of x divided by the marginal utility of y. Marginal utility of x, the partial with respect to x is just 2. Partial with respect to y. The derivative of the natural log is 1 over the whatever's here multiplied by the derivative of this argument. The derivative of this is just 1, so it's going to be 1 times 1 over y, but we had this coefficient 3 here, so it's going to be 3 over y. 2 divided by 3 over y gives me it gives me my marginal rate of substitution, so that's 2y over 3. I'm going to compare that to the price ratio, which is 6 over 1. And then solving really quickly, we find that we find the optimal amount of y is 9. And then using my budget constraint, if I consume 9 units of good y, and I have $18 available, that gives me the ability to buy 2 units of good x, given the price of good x is 6. All right, now find the optimal bundle if the consumer has income of 9 and faces the same prices. So suppose I have much smaller income. Now what am I going to do? Well, the margin rate of substitution and the price ratio, those are still the same as before, right? But when I go to my budget constraint, I've got an issue here, and that is if I'm spending 9 units, or my expenditure on good y is 9, I've already exhausted my budget, so I'll consume none of good x. All right, so now find the optimal bundle if the consumer has income of 6 and faces those same prices. Now what do I do? Well, the problem is I can't afford y equals 9. So what I'm going to do is I'm going to buy as much y as I can. And then if you compare the marginal rate of substitution at that bundle versus the price ratio, we're still at our alley solution, our all y solution. So what I'm going to do is I'm going to realize that with this type of quasi-linear preferences, my consumer really wants to have 9 units of good y. They can't afford it. They're going to buy as much as they can. They're going to get 6 units. Let's evaluate my margin rate of substitution if I have 6 units of y. So that's going to be 12 divided by 3 is 4, which is less than my price ratio. Right, so my indifference curve is flatter than my price ratio, or my budget constraint, which gives me my alley solution. What that's telling me is if I give this consumer more income, then I'm going to put it towards good y. Matter of fact, like we know that already, if we gave this consumer 3 more units of income, they're going to buy this bundle, right? Okay, part 8. So here's a Lagrangian. Consider a consumer with utility represented by x to the 2/3, y to the 3/2. This is Cobb-douglas. This is Cobb-douglas utility maximization. So I wrote up my consumer's utility maximization problem. So utility function minus lambda times the budget constraint. I take my partial derivative with respect to x, partial with respect to y, and then partial with respect to lambda. Partial with respect to x, so it's going to be 2/5 x to the minus 3/5, y to the 3/5. Don't forget this y to the 3/5 comes along for the ride. It's like a constant. Just like if you had 2x squared and took that derivative, well, you'd have 4x because the 2 out front comes along for the ride. Same thing here. Relative to when I take a partial derivative with respect to x, this y is a constant. So it stays there. Same thing when I take this partial with respect to y, it's going to be 3/5 x to the 2/5, y to the minus 2/5. Because x to the 2/5 is a constant. It's almost like a coefficient when I take the partial with respect to y. So it comes along for the ride. When I simplify this out, right, so this is like bang for your buck principle. This is marginal utility of x divided by price of good x, marginal utility of y divided by price of good y. Cross multiply gives me literally the MRS equals price ratio. And then solving, I find the relationship between them at the point of, where we'll get our tendency. I substitute this into the budget constraint, and I solve for my demands. These are Marshallian demands. This is going to give me my optimal amount of good y as a function of income and price of good y. Optimal amount of good x as a function of income and price of good x. Right? True or false, this consumer always spend 2/5 of their income on good x? Yeah, we have this right here. So if I multiply through by px times x, then I've got my, I've written the expenditure on good x equals 2/5 of my income. And here's my expenditure on good y. Got that from my demand for y. It's 3/5 of my income. And the rest are just working with that principle. Well, the rest of this question. So true or false, regardless of what happens with good y, if income is 40 and price of good x is 4, the consumer will buy 4 units of good x. Yeah, you could verify this with the demands that we have above, and it's true. And then right here, regardless of what happens with the good x, if income is 40, price of good y is 6, consumer will buy 6 units of good y. Consumer will buy 4 units of good y. And you can also verify the proportion of my income that I'm spending on good x and good y in both those cases. Lastly, it doesn't matter how much the consumer is currently consuming. They'll always be willing to trade good Y for X at the same rate. No, my MRS depends on my current bundle, right? So this right here, true or false, like this statement, if this was true, I would have to have perfect substitutes preferences. Okay. All right, the last one, examine a consumer's budget constraint with the following conditions. Consumer has $30, there's two goods, X and Y. Well, the price of good Y is 2 no matter what. The price of good X is governed by the following scheme. Consumer has a coupon that reduces the price of the first 6 down to 1. Consumer pays the full price for all subsequent units. Okay, what's the budget constraint? Remember, for these, I think it's best to first find the vertical intercept. Find the one that's, because price of good Y is always 2. So I'll just divide my income by 2 to find out that if I spend all my money on good Y, I can buy 15 units. Next thing to do is find out how much money have I spent by the time I get to the kink, to the place where this thing changes slope. Well, I mean, also, you might want to find out what those different slopes are going to be. So the price ratio is going to be 1/2 for the top part because, Y is always 2 and the price was initially 1, right? And then it's going to be 3/2 for the bottom part because the price of good X goes to 3. All right, so, but I want to find where that kink is, where it switches from a slope of 1/2 to 3/2. So that happens when I've bought 6 units. Those 6 units are going to cost me $6 because the price of good X was 6. So I could spend $6 and get to here. If I do that, I have 12. If I spend $6, I have $24 remaining. I could spend those $24 on good Y. $24 divided by the price of 2 allows me to buy 12 units of good Y. That's how I found this point. Or after spending $6 to get those first 6 cookies, I could spend the remaining budget on cookies. I've got $12 remaining, remember, but now it's going to be $3 each. So 12 divided by 3 is 24 divided by 3 is 8. 8 plus 6 is 14. All right, so that's that part. If the consumer's utility is given by these perfect substitutes preferences, what value of beta guarantees that we have the alley solution and consumes only good Y? Okay, so we need something that's going to give the slope of my indifference curves a slope that's flatter than a slope of 1/2. So beta's got to be bigger than 4. If beta's bigger than 4, then 2 divided by something bigger than 4 is going to be flatter than 1/2. Right? The denominator is going to be bigger than the numerator. Well, we already knew that's going to be the case, but it's going to be, the denominator is going to be more than twice the numerator, so that'll give me a slope that's flatter than 1/2. That would guarantee my all Y solution. Find the optimal bundle for a consumer with preferences represented by the following perfect complements in difference curves. So this, remember, we could place the comma with an equal sign and find the ray through the origin that connects all the corners. So that's going to be the line Y equals 2X. We could plug that into our budget constraint. That's a little bit hard to do because of this particular budget constraint. But if we look at this and if we're really clever, oh, wait a second, the 0.612 lies on this line. And so it's actually going to go right through here. All right, so that was I thought that was clever. Anyway, I hope you enjoyed the video. Hope you enjoyed the exam. Hope this helped you, and I'll see you next time.